Thank you for your kind invitation, and thank you for your kind introduction, and thank you for staying with me until the last day of this wonderful conference. So today I will talk about the multireference quantum chemistry development of the multireference quantum chemistry theories. I became independent 4.5 years ago, and I will talk about the works I have worked on in the last 4.5 years. So let me start. So probably everyone in this room will probably know that there are two main issues in CAS-SCF calculations. First, the dynamical correlation is missing and energy is quite off from the experimental value or whatever. So I will talk about my work on the perturbation theories, multireference perturbation theories. There was wonderful talk by Professor Plasser on MRCI theory. And second, if we perform embedding in CAS-SCF, we embed full CI space in mean field. So that is kind of embedding. But full CI space has limitations like up to 16 electrons in 16 orbitals, right? So I worked on some methods that can expand the full CI space by approximation. And there was also a wonderful talk by Professor Piekuch in the first day. And also there were some works by Professor Luz, who talked in the first day, I think. And so why is this needed? We can just do some active space calculations with reasonably small active space, but with physical reasoning, right? But that might be not the case for some systems like iron porphyrin. We have 10 electrons in 9 orbitals active space, and that is physically reasonable. We have all 3D orbitals included in active space, and 4 orbitals on porphyrin ring is also included in that active space. So that is physical, and one might think that CAS-PT2 calculation will recover all the dynamical correlation, hopefully, and then the calculation would be right, hoping that it is right, but the results show that it's not. The competitive energy level shows the singlet ground state, while the experimentally singlet should be up high in terms of energy. So that is wrong. So we should expand the active space. So I will talk about these two things I have worked on in the last 4.5 years. So first thing I will talk about is the multireference perturbation theory for exploring potential energy surfaces. So basically, I'm a person who worked on the analytical gradient theory. So undergraduate quantum chemistry textbook said that from the Hartree-Funk reference, we can include dynamical correlations using configuration interaction, perturbation theory, and coupled cluster. That is what they say in the undergraduate quantum chemistry textbooks. Of course, there are many other the wonderful methods, but this is what undergraduate quantum chemistry textbooks say. So with the multireference theories, basically the situation should be same, while there are some problems on MRCC that Professor Plasser mentioned. There is MRCI, there's MRPT, and MRCC can be defined at least. But MRPT should be cheapest, as you know that among the CISD and MP2 and the CCSDT, the MP2 is the cheapest. As MP2 is cheapest, for MRPT, the MRPT should be the cheapest, but due to the computational burden, the applicability of MRPT was quite limited until recently. So for dynamic simulation and geometry optimizations. What is MRPT? MRPT2 is the second order perturbation theory, and it is probably the cheapest while yielding reasonable accuracy. So in perturbation theory, probably everyone in this room should know that the perturbation theory separates the whole Hamiltonian into mean field part and the perturbation part. And then we have second order correction to the energy, and probably the first order correction to the wave function. There are many definitions for MRPT depending on the definition of zeroth order Hamiltonian and basis function for expanding the wave function, which is MCQD-PT2, MSKS-PT2, QDNF-PT2, and DSRG MRPT2, which is derived from somewhat slightly different contexts. But anyway, I will talk about the developments on these theories, the analytical gradient theories, on these methods. So this is work from the 5 years ago while I was doing my postdoc with Professor Toru Shiozaki, and I did CAS-PT2 dynamic simulation of JP Chrome for non-adiabatic dynamic simulation. And there are two channels which are responsible to the deactivation of the excited state. And the CAS-SCF simulations normally prefer the P channel to be responsible to the non-adiabatic decay. But the thing is that when we include the perturbative correction and do the simulation, the I channel is almost equally responsible to the non-adiabatic decay. So this is why we should include the dynamical correlation to the multireference calculation in some way. The way that I use is perturbation theory. So this was 5 years ago, and I applied the analytical gradient methods for conical intersection optimizations using CAS-PT2, NEF-PT2, MCQD-PT2, and state average DSRG MRPT2. So basically, the conical intersection optimizations are possible, and the including dynamical correlation really changes the results. So we should include the dynamical correlation when we are considering this kind of system. So the developments that made this kind of calculation possible is like this. So the applications in dynamics and optimizations require nuclear gradients and probably non-adiabatic coupling between the states. And you need derivatives, right? So if you want nuclear gradients, we can always do this kind of numerical differentiation, right? But the thing is that this requires 6 NA-LUM energy evaluations. So we need analytical gradient. This is trivial, right? And how can you derive the formalism for analytical gradient? We can recast the formula for energy to the function of some variables, in this case, orbital coefficient, CI coefficient, and perturbation amplitude. And then using the chain rule, we can derive the analytical gradient like this. We have some partial derivative of energy with respect to the nuclear position, and there are also partial derivatives with respect to that variables multiplied with the derivatives of the coefficients with respect to the nuclear position, like this. So we need this kind of derivatives of the coefficient with respect to the nuclear position. And what can you do? Historically, we can always do numerical differentiation, but that should be not the case, because if we can do numerical differentiation of that kind of variables, we can just numerically differentiate all the energies. So we can solve the coupled part of the equations. This is more efficient than numerical differentiation, but we still have to solve 3n linear equations. So this is cheaper, but still it is not fully optimized. So the Handy and Schaeffer wrote wonderful paper on Z-vector inversion. So this made for the analytical gradient evaluations, you have to solve only one linear equation to evaluate this kind of analytical gradient. And then the Lagrangian formalism can be formulated so that you just set up a Lagrangian, and then the solving for the Lagrangian multipliers will automatically lead to the Z-vector formalism, so that you can evaluate the analytical gradients. So this is the theoretical developments done in like from the 50 years ago to the 20 years ago. And then I applied the Lagrangian formalism for various perturbation theories, multireference perturbation theories. So you treat convergence conditions for the variables as a constraints in Lagrangian multiplier like this. And then you construct the Z-vector equation by like this. And then you solve for the multipliers. And then you can obtain the analytical gradient like by just taking a partial derivative of the Lagrangian with respect to the nuclear position. So the main difficult part of this kind of work will be deriving the equations for source terms for these kind of Z-vector equation, and I derived the equations for the various MRPT2 theories, and this the equations look like this, and there are some conditions depending on the theories. For example, MCQD-PT2 and DSRG-MRPT2 should include the semi-canonical condition for active orbitals, so that should be coupled with the Z-vector equation. So basically, there are some technical advances that is associated with this development, but basically the main work that to be done is the deriving this kind of equation. So I derived this kind of equation and implemented it to the computer code, and then it made possible to perform conical research or molecular dynamic simulation using this kind of perturbation theories. Of course, these MRPT2 theories don't solve all the issues on the multireference calculations, all the issues in CAS-SF. There is the so-called intruder state problem for CAS-PT2 and MCQD-PT2, and you add some shift parameter in CAS-PT2, real or imaginary, or the so-called ISA parameter, which actually Professor Witek worked on in like 20 years ago. And the results depend on this kind of the shift parameters. So the parameters should be chosen carefully. And in multi-state CAS-PT2, the zero-order Hamiltonian, the definition of zero-order Hamiltonian is different. In both cases, the default zero-order Hamiltonian is state-specific Fock operator, while in both port, the default zero-order Hamiltonian is state-average Fock operator. So this leads to the changes of the conical section structures like this. But I should mention that there was a wonderful theoretical advance by Professor Lind's group on that developed the XDW CAS-PT2, which mixes this kind of Mokes type zero-order Hamiltonian and Mopor type zero-order Hamiltonian. DEV-PT2, there is some failure on the evaluating the potential surfaces near the CAS-SF the conical sections. There is some anomalies on the potential surface, so you should be careful when you are considering the conical sections computed by the CAS-SF, not PT2. And DSRG-MRPT2 strongly depends on the DSRG-MRPT2 results strongly depend on the flow parameter. So flow parameter should be chosen carefully. So that is the main issues. But the methods have pros and cons. So we should select the method carefully and the basic parameters carefully when doing the multireference perturbation theory calculations. So I will summarize the first part of my talk. So MRPT excited state dynamic simulations are now routinely possible with the analytical gradients. And I developed the new gradient algorithms for the FPT2, MCQD-PT2, DSR-MRPT2. And I think there are still some rooms for developments, including possibilities for expanding the active space. And what I'm doing now, what in progress is that I am developing analytical gradient methods beyond the MRPT theory. The computational power have grown, and now the calculations beyond MRPT2 for large system is now possible. So I'm developing some analytical gradient theories for that. So this was the first part of my talk. And the second part will be treating the large active spaces. So ASCI method by Professor Martin Head-Gordon and coworkers can be embedded in the mean field to result in the ASCI SF method. And other selected CI variants can be, of course, embedded in the mean fields to the result in HBCI, SCF, SCI, SCF, CIPC, SCF, whatever. So, but the cell SCI, SCF orbitals are somewhat difficult to converge compared to CAS-SCF because the CI space is now truncated and the energy varies with respect to the changes in the active orbitals, which is mathematically the gradient with respect to the active-active rotation is not zero. So I first implemented the second order orbital optimization schemes, augmented Hessian and Werner-Meyer-Knowles algorithms, so that I can facilitate the convergence of the orbitals with respect to the number of super macro iterations. Actually, this one super macro iteration corresponds to 10 macro iterations. So it is like 200 macro iterations. So it is quite many, but you can still converge the orbitals with the SCF, SCI, SF methods. And probably the optimized orbitals physically mean that the orbitals will be the orbitals for the most compact CI expansions, probably. So I tested some ASCI-SF convergence for this kind of iron porphyrin active space, iron porphyrin, 32 electrons in 29 orbitals, and 6 PERISN, which has 52 electrons in 52 orbitals, like this. And I saw the convergence, and the active space is still correct physically, and the energy for iron porphyrin is now somewhat correct. Then the truncated CAS-SF, and I proceeded to geometry optimization. The ASCI-SF energy is partially variational with respect to the CI coefficient and orbital coefficient, and CAS-SF analytical gradient routine can be used for ASCI-SF. So I optimized this kind of system, and I evaluated some adiabatic gap energies like this, and it was possible. This is simple version. And more complicated version, actually, the cell SCI energy can be corrected for the contributions from the rest of the FCI, which is not included in the truncated CI expansion by perturbation theory like this. So, and this PT2 corrected energy has one useful property, that the energy is almost linear with respect to the PT2 correction energy. And when you linearly extrapolate this perturbative correction, you get the energy that is very close to the true full CI energy. But the PT2 corrected energy is now not variational with respect to the orbital rotations and CI coefficients. So the Z vector equation should be solved like this. And this is the result. First, you can compare with the CAS-SF always for the systems that CAS-SF is tractable. And I tested for this kind of system. And the one thing is that you can also extrapolate the analytical gradient so that you can reach the almost CAS-SF level gradient. And the geometric optimization using the extrapolated gradient yielded almost the same geometries as with the CAS-SF geometries. And you can also evaluate the number of unpaired electrons in system like this. And then you can obtain this kind of expectation, the extrapolated values, which are pretty close to the CAS-SF values. So like difference of 0.001. So this is reasonable. And of course, you can optimize the geometries for this kind of large the systems with the large active space. And this kind of calculations was possible with the extrapolated analytical gradients. And to get hopefully the near CAS-SF level geometries. So I developed the analytical gradient algorithm for ASCI SF and ASCI SF PT2. And I think I developed for ASCI, but I think this can be expanded to all the SCI the algorithms, and with extrapolations, near exact CAS-SF level geometries and physical quantities like the number of unpaired electrons can be obtained, and active space can be as large as 50 electrons in 50 orbitals. And what I'm now working on is developments on the excited state optimizations and dynamical correlation methods. So this is it, and I was supported by NRF, POSCO, and Chungbuk National University. Thank you so much for your kind attention.
Thank you for this nice presentation. Questions, Sergey?
I have two, but closely coupled, I think. So, so first of all, the first one is about the porphyries we talked about. Maybe I will jump very quickly. So, did you solve the problem about orbital states with the large active space, or is it still persists?
With the expanded active space, I think the problem of the spin state is somewhat solved, because now we don't have at least the singlet ground state. Singlet is up high, so I somewhat solved the problem with the expanded active space, I think.
So it's rough. So it's pretty right. Okay. All right. So the and the closely coupled one. So for this type of system, so always, I mean, while I'm not questioning the value of the doing very large active spaces when you have a universe, right? So and especially for your last sort of examples with this, that's certainly the case. But for porphyrin type systems, so the active space you show, I mean, makes perfect sense in terms of degeneracy, right? So when you're talking about like four, what is called Guterman orbitals, So I wonder if increasing the active space is the requirement for large active space is just related to the perturbative nature of perturbation, custody 2 or perturbation theory you use. And if you use something like MRCI, for example, you get away with a small active space and still get the correct orbital states. What do you think about that? Because
maybe that would be the case. I think the PT2 tends to overcorrect the dynamical correlation when the orbitals are near degeneracy, like this kind of porphyrin pi orbitals are near degeneracy, and I think the tends to overcorrect the energy, I think. And that is why that is the reason for the wrong spin state energies, I guess. But with MRCI, even though I didn't try that, it might be the case. I don't know, because I didn't try the MRCI calculations with this system.
Sure. Yeah. It's just makes me wonder, right? So I mean, the whole idea of the small dynamics of static correlation, that's a account in James. If you don't have a degeneracy.
Mhm.
The question is why do we need such a huge active space, right? And I think that's come from the fact with perturbative nature, basically. Things. And you wouldn't probably include the states, right? So,
Maybe.
so and if you do an RCI, you probably, I think, can get away with small kinds of like physical active space, right? But of course, it's much more expensive.
Yeah,
right?
much more expensive. That's true.
Thanks. Very cool talk by you.
Thank you.
Nice work.
Elfie?
So very impressive work.
Yeah.
I'm probably too demanding. I'm interested in vibrational spectroscopy. So what is your perspective on getting analytical Hessians
Analytical Hessian.
at some point?
So the thing is that for CAS-SF, there is a way to evaluate the analytical Hessian non-variational CAS-SF. But then if you have the ASCI SF PT2 or the CAS PT2, the analytical Hessian, the expressions for evaluating analytical Hessian should be very complicated. And even if that's possible, you will solve all the coupled part of equations, so it is not that easy. Actually, the one interesting results on the the vibration frequency that I got is that with CAS PT2, actually, you have you have to diagonalize. You have to get the the orthogonal basis, and you have to get rid of linear dependency in the basis. So you have some kind of threshold, and depending on the threshold, with the numerical Hessian, there is some spurious imaginary frequency that you get. So you should be somewhat careful when you are evaluating the CAS PT2, the numerical Hessian. So that was what I got related to the vibration frequencies.
Thank you.
Joe, there is a question from online participant Rob Lavrov. What methods are you most interested in working on after MRPT2 methods for gradient? MRCI?
Yeah, that would be PT3. PT3 is one of the targets, and I have some other targets like AC or adiabatic connection, or the adiabatic connection is cheaper than MRPT, by the way. And then the variance of MRCC, if I have some capacity to work on it. I don't have capacity actually for the MRCC actually, but yeah, that is what I'm hoping for.
Good, thank you very much. Let's thank the speaker again.